Let me apologize in advance that I don't have a theorem to bring you. So I'm going to bring you a lot of speculations. So what I want to do in this talk is first tell you about the speculations, and then give you an idea about why you might be interested in them, and then give you an idea of why you might be inclined to believe them. So let me start. Well, throughout this lecture, P is a fixed prime number, and a lot of things that I'm going to talk about are implicitly P-completed, and a lot of constructions that I'm going to talk about are implicitly derived. So if you're wondering in your seat, you know, does he really mean, should that be a derived tensor product, or should that be P-completed? The answer is yes, and I might not mention it. So I want to talk first about the theory of Syntomic cohomology. So let me remind you that if you have a scheme in which P is invertible, then you can talk about its p-adic étale cohomology in weight n, meaning you have a Tate twist here. And that Tate twist is something that a priori only makes sense when P is invertible in the theory of étale cohomology. And the theory of Syntomic cohomology is an extension of this invariant in a sensible way to all schemes. So in an invariant which makes sense, for example, schemes in which P is 0, and things like, well, not schemes, but formal schemes in which P is topologically nilpotent. And I'm going to focus, as I promised, on the P-complete case, meaning I'm talking about p-adic formal schemes, and then so those have Syntomic cohomology groups, and here I mean Syntomic cohomology in the sense that was recently introduced by Bott, Morrow, and Schulze. So this is a variant of an earlier theory. The idea goes back to Fontaine and Messing, which their theory really only worked either when you work with rational coefficients or when the weight is small. And this theory seems to be a sensible thing to do integrally in all weights. So these Syntomic cohomology groups are the cohomology groups of a chain complex. So I'm going to denote that chain complex by R gamma sin x, zp of n. So yesterday, Toby talked about the theory of prismatic F gauges. So prismatic F gauges, those are the coefficient objects for this theory of Syntomic cohomology. So let me just mention what I think of as the primary motivation for studying them, and that's that you would like to have a Kunith formula. So let's say you had p-adic formal schemes x and y, and you wanted to say something about the Syntomic cohomology of x cross y. So there isn't a simple formula that says, that like you have in topology, that says you just take the cohomology of x and the cohomology of y and tensor them together. And the theory of prismatic F gauges is the fix for that. So if you want a Kunith formula, then you want to think of Syntomic cohomology as given by a two-step construction. So first you input your formal scheme x, and then to that formal scheme, where's my pointer? No. Well, to that formal scheme, you associate an object which I'm going to denote by z prism superscript x. So that is an object of a category that I'm going to write as F gauge prism, the category of prismatic F gauges that Toby mentioned in his talk. And this is an object which depends contravariantly on x. So it's some incarnation of the motive of x, but cohomological motive. It's some version of the cohomology of x. And then in the category of prismatic F gauges, you can consider homs from the unit object into this z prism x. So the unit object I'm just going to write as z prism. And then you can throw in a twist here if you want to look at different weights. And then that hom, computed in the derived sense, is some chain complex, and that chain complex computes Syntomic cohomology. So this is, here you can think of Syntomic cohomology as given in a two-step process, and the reason that you might want to compute it is that the first step of this process satisfies a Kunith formula. If you take the product of x and y, well, this z prism of the product is the tensor product of z prism of the individual factors. So this step satisfies a Kunith formula, and that's lost only when you take homs out of the unit object. So that's one reason that you might be interested in this category. Another reason is that they serve as coefficient objects for the theory of Syntomic cohomology. So every object in this category of prismatic F-gauges can be thought of as giving you a cohomology theory on p-adic formal schemes. And namely, if you want to, something you might think of as Syntomic cohomology with coefficients in E. So what you do is you input X, and then you output X in this category of F-gauges from the unit object into this cohomological motive of X, but tensored with E, where E is the coefficient object that you're interested in. And lots of interesting cohomology theories are special cases of this construction for varying choices of this E. So for example, the de Rham cohomology of X and all the stages in its Hodge filtration can be constructed this way. The crystalline cohomology of the special fiber of X and all stages in its Nygaard filtration can be constructed this way. The prismatic cohomology of X comes about in this way. And of course, the Syntomic cohomology of X comes about in this way, where you take E to be certain invertible objects. And so you can think of this category of prismatic F-gauges, it's some collection of cohomology theories that kind of feel like these ones. Cohomology theories for p-adic formal schemes that feel like they're made out of differential forms in some either more or less indirect way. But the subject of this talk is that there are other cohomology theories that feel like this, but that don't come from prismatic F-gauges. So an example is things that are related to K-theory, things like topological cyclic homology or topological Hochschild homology that are very useful tools for computing algebraic K-theory. These are also closely related to differential forms. There's work of Bott-Morrow-Schulze, for example, telling us that there's a spectral sequence where the input is Syntomic cohomology and the output is the topological cyclic homology of X. Well, this is more or less built into their definition of Syntomic cohomology that I mentioned earlier. So you could think of topological cyclic homology and these variants. They're also cohomology theories on, let's say, p-adic formal schemes that are somehow built by thinking about things like differential forms, but they don't come from prismatic F-gauges because they're in some sense not linear enough. These topological cyclic homology groups, those are the homotopy groups of a spectrum, but that spectrum in general is not an Eilenberg-MacLane spectrum. Doesn't come from a chain complex. And so the goal of this talk is to speculate about an enlargement of this category of prismatic F-gauges, which contains more coefficient objects. It contains coefficient objects for cohomology theories that are like these. And so let me start by, just as a warm-up, not talking about algebraic geometry, but just talking about how this works in ordinary topology. So in ordinary topology, we study the stable homotopy category. I'm going to denote that by SH. So this, in Tomer's talk, was the category of spectra. And the objects are things that you can think of as cohomology theories on ordinary topological spaces. And in particular, you get examples of objects in the stable homotopy category that correspond to ordinary cohomology. So if you have an abelian group A, you can talk about the cohomology of a topological space with coefficients in A. That's an example of a cohomology theory. It comes from an object in the category SH, which is typically denoted by HA. And if A is a ring, then HA is also a ring, or it's an algebra in this category SH. And if you study modules over this algebra, then you get something that are much more familiar. So modules over HA in the stable homotopy category can be identified with the classical derived category of chain complexes of A modules. And that identification is by essentially taking an A module to the associated cohomology theory or the extension of that to chain complexes. So in particular, if you're interested in modules over HZ in the stable homotopy category, that's the derived category of abelian groups. That's something that looks like chain complexes. So this is the story in ordinary algebraic topology, and now I would like to bring this story to algebraic geometry. And so the conjecture in a very vague and broad form is that there's some counterpart of the stable homotopy category in p-adic geometry, what I'm going to call the prismatic stable homotopy category, SH prism, and it should be related to the usual stable homotopy category as the category of prismatic F gauges is related to derived category of abelian groups, or as related to chain complexes. And so this is going to be in the symmetric monoidal category. There's some notion of tensor product, and the tensor product has a unit, which I'm going to denote by S sub prism. OK, so what I'd like to do for a large portion of this talk is just expand on this conjecture. I want to tell you a lot of features that I want this SH prism to have. I want to tell you what it ought to look like. OK, so the first thing I want is that it's related to the category of prismatic F gauges. So this category SH prism, in addition to its unit object, which I'm calling S prism, it should contain an algebra that I'm going to call Z prism. And if you look at modules over Z prism, you should just recover prismatic F gauges in the sense of the very second slide. And this you should think of as a prismatic analog of the statement that I made just a little while earlier, that if you look at modules over this HZ in the stable homotopy category, then you recover the derived category of abelian groups. So another feature that this stable homotopy category should have is that it's related to cohomology theories. Now we're not talking about cohomology theories on ordinary topological spaces. We're talking about cohomology theories on p-adic formal schemes. So let me explain how this relationship is supposed to work. To every p-adic formal scheme X, there should be associated an object that I'm going to call S prism to the power X. And this is, again, some incarnation of the motive of X in this world, but it's a cohomological motive. It's a contravariant functor of X. And so this should be some object in the prismatic stable homotopy category. And in particular, you can take that object, tensor it with your favorite other object, E, and then consider Homs from the unit object into that tensor product. That's going to be some invariant of X that you can think of as a cohomology theory that depends on E. And this should be related to the story that I told you earlier. Namely, if you take S prism X and you tensor it with Z prism, so now you have a Z prism module, something that you can think about as a prismatic F gauge, that should be the incarnation of X in the world of prismatic F gauges. And meaning, meaning that when you restrict this construction to the case where E is module over Z prism, you recover the earlier picture where every prismatic F gauge determines a cohomology theory. So this is some larger class of cohomology theories that are somehow allowed to be a little more nonlinear. And if X is a smooth, in general, let me say, this is an incarnation of the cohomology of X. You don't expect there to be an incarnation of the homology of X. That is, you don't expect these objects S prism X to be dualizable in general, but they should be dualizable when X is smooth and projective over ZP. And in that case, this has a dual, which I'm going to denote by X with brackets around it. So this is some incarnation of the homology of X, which lives in this prismatic stable homotopy category. And as an example, you can consider the motive of P1, and that should split as a sum of two pieces, namely the unit object and some other invertible object which plays the role of a Tate twist. So this prismatic stable homotopy category should also be related to K-theory. Namely, it should contain an object that you can think of as the prismatic incarnation of K-theory. So I'm going to call that KU prism. And that object should represent the cohomology theory topological cyclic homology in the sense that I described earlier, that when you extract a cohomology theory from this, you get TC. So actually, I want to consider a stronger speculation, or a stronger version of that. If you look at modules over this KU prism, that should have a different description, or a more classical description, as cyclotomic spectra that are modules over the topological Hochschild homology of Z. And under this identification, if you take the motive of some x, and then you tensor it with this K-theory representative, you get a module over KU prism. So you can think about that as a cyclotomic spectrum, which is a module over THH of Z, and that module should be THH of X. And now, if you believe this, well, from the Nikolaus-Schulze point of view, TC of X is defined as, in two steps. First, you take THH of X, which is a cyclotomic spectrum, and then you consider in cyclotomic spectra Homs from the unit object into that. So that's the same thing as Homs of THH Z modules in cyclotomic spectra from THH of Z into THH of X. So that's the same thing as Homs, but if you believe this equivalence, that's Homs in the stable homotopy category from the unit object into KU prism tensored with the motive of X. So that's just a proof, if you believe this, that this KU prism represents TC as a cohomology theory. So another feature that this this prismatic stable homotopy category has is that it should have a nice spectral decomposition. So let me remind you of something that Toby mentioned in his talk, that this category of prismatic F gauges, it's the derived category of a certain stack in algebraic geometry. This stack was introduced by Drinfeld, but I'm going to follow Bargov's notation for it, ZP sin. So that's a stack on the category of commutative rings, and its derived category is the category of prismatic F gauges. And this prismatic stable homotopy category is some fancier version of the category of prismatic F gauges, and it should have a similar description. It should be the derived category of a stack, but now it's not a stack on the category of commutative rings anymore. It's a stack on the category of commutative ring spectra, meaning commutative algebras in the stable homotopy category. But this is some kind of fancier notion of a stack, but it's a sort of enhanced version of the original ZP sin in the following sense, that if you have a commutative ring R and you want to know the R valued points of ZP sin, those are the same as the HR valued points of this enhanced version of ZP sin. So this stack contains all the information of the original ZP sin plus a little bit more because we're allowed to evaluate it on commutative ring spectra that are not of this form. And, well, by some version of Tanaka duality, the data of the prismatic stable homotopy category and the data of this stack that it is the coherent derived category of, those are really the same. They're interchangeable. If you have either one of these objects, you could use it to construct the other. So why am I mentioning this? Yeah, also a version. I'll say something about that in 1 second. Yeah, well, not quite that, but something you'll see. OK, so why describe the category of prismatic F gauges this way? What's the point of ZP sin? And the point is that there are a lot of interesting loci in ZP sin, meaning there's a lot of interesting maps into it from things that you might understand better. And anytime you have a map from some algebra geometric object into ZP sin, you get a cohomology theory on formal schemes. This is really a variant of the construction that I told you earlier. Namely, you take the motive of X, which is a prismatic F gauge, you pull it, you think of that as a sheaf on ZP sin, you pull it back to T, and then you take the global sections. You take either the chain complex R gamma, or you take the hypercohomology groups if you want abelian groups. So every locus in ZP sin determines a cohomology theory, and, well, something I mentioned earlier, the point of prismatic F gauges is that you have a Kunith formula. So in particular, if T was spec R, if this was an R-valued point of ZP sin, then you would get a cohomology theory valued in R modules and one that would satisfy a Kuhneth formula. That product of p-adic formal schemes, your cohomology theory took that to a tensor product, now derived tensor product of chain complexes over R. So this ZP sin, you should think of the points of it are like cohomology theories on p-adic formal schemes that satisfy Kuhneth formulas. And the failure of Syntomic cohomology itself to satisfy a Kuhneth formula is because this is very much not an affine scheme itself. It's Syntomic cohomology is made out of cohomology theories that have Kuhneth formulas, but by taking some big inverse limit, but the inverse limit loses the Kuhneth formula. But let me mention, lots of cohomology theories are interesting. Cohomology theories come about in this way for different values of T. So for example, this stack has an underlying topological space. That underlying topological space is very boring. It has 2 points, one of which is an open point and one of which is a closed point. But that sounds boring, but it's not that boring because, for example, you could take T to be the open point, and that corresponds to a cohomology theory. And that cohomology theory has a name. That's prismatic cohomology. You could take T to be the formal completion of this object at its closed point. And that also, cohomology theory also has a name. It's also prismatic cohomology, but now completed with respect to its Nygaard filtration. And, well, there's a divisor inside well, not ZP sin, but ZP Nygaard with a corresponding cohomology theory called Hodge-Tate cohomology. If you don't know what any of these things are, this probably doesn't mean anything to you. But here's one that you're probably familiar with. de Rham cohomology is what you get by applying this construction to a particular ZP valued point called the de Rham point. And, well, de Rham cohomology has a Q deformation that comes out of the theory of prismatic cohomology. And that comes also about from this construction by taking not the de Rham point, but a certain one parameter deformation of the de Rham point. So lots of interesting cohomology theories arise via this construction. That's one reason you might want to understand the geometry of ZP sin. And what I want to say about this fancier version of ZP sin is that all of the loci that I just mentioned are inverse limits of loci that live in this enhanced version. So they all have counterparts, inverse images of, they all have enhanced counterparts, and those could be used to give other examples of cohomology theories. So for example, rather than taking Z prism X and restricting to T, you could take the K-theoretic incarnation of the motive of X, this thing I called KU prism, tensored with S to the X, and you could restrict it to this enhanced locus. And if you do this, you again get cohomology theories that have familiar names. So when you restrict to the open point, you get what's called topological periodic cyclic homology. Or, well, that's not quite true for general X. You really get some kind of decompleted version of it. When you take the formal completion at the closed point, you get TC minus of X. If you take the Hodge-Tate divisor, that corresponds to topological Hochschild homology. If you take the de Rham point, that corresponds to ordinary periodic Hochschild homology. And, well, the Q line is maybe a little bit interesting. You get some variant of TP. Up to a pullback along Frobenius. And the point is, it's an interesting suite of invariants. These are invariants, except maybe for the last one, that people who study K-theory really want to know about. And this is just what you get from studying this particular object KU prism. So these are existing invariants, and I'm speculating that actually they participate in a much larger class of invariants that you could get by just, in this formula, replacing KU prism by other objects in the prismatic stable homotopy category. So any other object in the prismatic stable homotopy category has its own version of TP and TC minus and THH and so forth. That's what this speculation is saying. Yeah. This is non-connective KU prism. Yeah. There's also a connective version. I mean, the Postnikov filtration on KU has to do with the BMS filtration on all of the invariants I just mentioned. Yeah. All right. So that's all well and good, but what are the possibilities for what this SH prism should look like? So let's consider first a stupid candidate. So our first candidate is take the category of prismatic F gauges and just take S prism and Z prism to be the same. You could make that definition. And it's compatible with the demands that I've made so far, except for the one about K-theory, right? I said I wanted TC to be representable by an object of SH prism, and that's not possible if you adopt this as your definition, because the cohomology theories that come from prismatic F gauges, again, they're too linear. So a better case is to take S prism to be what you might think of as the connective version of the K-theory spectrum. I think something Akil was alluding to. And in that case, there's a candidate for definition which would kind of make this statement true, which is you take your prismatic stable homotopy category. Well, I said if you wanted modules over non-connective K-theory, periodic K-theory, you should take THHZ modules in cyclotomic spectra. If you want the connective version, then you should consider the filtered version of that, THHZ modules in synthetic cyclotomic spectra. So this is a notion that's recently been studied by Ben Antiu and Noah Riggenbach. I don't know if they were particularly focused on THHZ modules, but there's a definition here which would satisfy all of the requirements that I've made so far. And it's not what I want to propose. And that's because this is not how homotopy theory works. In homotopy theory, we don't just, this is like saying the only cohomology theories are K-theory and ordinary cohomology, and they're related by some spectral sequence, and that's it. But that's not how ordinary homotopy theory is very rich in cohomology theories, and I would like to speculate that the prismatic variant of stable homotopy theory should be equally rich. So I want to articulate that more precisely. So let me remind you, or if you've seen this before, that there's a notion in ordinary topology of a cohomology theory being complex orientable, which means that it has some theory of Chern classes for complex vector bundles. And there's a universal example of a complex orientable cohomology theory, which is called complex bordism. So that's represented by an object in the stable homotopy category that's denoted by mu. U stands for unitary. I don't actually know what M stands for. Someone can probably say. And this complex bordism spectrum, it can be built in a way that uses only ingredients that live in algebraic geometry. And as a consequence of that, it's something which should have if you believe what I've told you so far, will have a counterpart that lives in this prismatic stable homotopy category that I'm going to write as mu prism. So it's something that can be described as a direct limit over K of some twisted version of the motive of BGLK mod BGLK minus 1. What do I mean by this? Well, earlier I told you that you could take the motive of a smooth projective ZP scheme, and here these classifying stacks, their motives should be built as direct limits of the motives of Grassmannians. So I'm not going to elaborate on this construction. There's some way of mimicking the definition of mu in this category, and it will produce for you an object which you should think of in the prismatic stable homotopy category as playing the same role. It's now determines a cohomology theory on p-adic formal schemes, which is in some sense the universal example of one where you have a theory of Chern classes, now not for topological vector bundles, but for algebraic vector bundles. And there's a game that you can play whenever you have one of these cohomology theories, is that you can see what happens how these Chern classes for line bundles behave when you take tensor products of line bundles. And there's something, you can prove that there's always a formula here that tells you that the first Chern class of a tensor product of two line bundles can be written as some power series in the first Chern classes of the line bundles individually, where the coefficients of that power series determine for you a formal group law over the coefficient ring, over the cohomology of a point. And if you've studied one-dimensional formal group laws, the main theorem there is that there's a universal example of one-dimensional formal group law over the Lazard ring, which is a polynomial ring on infinitely many variables. So this data is classified by a map from a infinite rank, infinitely many polynomial ring on infinitely many generators to the thing that plays the role of the mu cohomology of a point, which is some, well, which I've written here. And well, let me tell you how this works in ordinary topology. There's a very important theorem proven by Quillen, which is that if you do the analogous construction in ordinary topology, you look at that formal group law that you get over mu, and it is the universal formal group law. In other words, this construction induces an isomorphism from the Lazard ring, a polynomial ring on infinitely many generators, to the mu cohomology groups of a point. And an essentially equivalent statement of that is that if you take complex bordism, in which you see these generators, T1, T2, and so forth, coming from the Lazard ring, and you mod out by them, then you just get back the Eilenberg-MacLane spectrum, Hz. So a way of saying this is mu is some kind of universal cohomology theory where you have Chern classes for vector bundles. When you form this quotient, that's like a universal theory where you have Chern classes for vector bundles and the usual formula for how they behave when you take tensor products. The Chern classes should just add. And the universal example of a cohomology theory like that is just ordinary cohomology. And so the way that I want to articulate that prismatic stable homotopy theory should behave like ordinary stable homotopy theory is that you should have the same phenomenon. If you look at the universal example of one of these prismatic cohomology theories that has Chern classes of vector bundles and mod out by the Lazard generators, you should just get Z prism. In other words, the universal such cohomology theory should be Syntomic cohomology back again. And let me say that there's an analog of this statement that you can formulate in motivic homotopy theory, and that's known as long as you're talking about doing motivic homotopy theory with coefficients that are invertible in the base. That's a theorem of Hopkins and Morel in characteristic 0, and I think Mark Hoywa extended that to just in general when you reduce mod p and p is invertible in your ground field. So that's not what we're talking about here. I'm talking really here about the case where we're interested in p-adic formal schemes, and we're interested in cohomology theories that have p-torsion information. And in that case, the analog of this theorem in motivic homotopy theory is not known, and that's the problem. If a theorem like this was known in motivic homotopy theory, then I wouldn't be bringing you conjectures, I would be bringing you constructions. Okay, so that's what I want to say about how this theory should work. That's what the speculation is, that there is this prismatic stable homotopy category with all of the bells and whistles that I just mentioned, and now I want to tell you why you might care about that. So let me go back to Quillen's theorem. It's essentially a reformulation of the calculation of this Steenrod algebra in ordinary topology. It's articulation of what all of the operations that ordinary mod p cohomology has. And if you understand that Steenrod algebra, you really understand the entire structure of the stable homotopy category. So it's not like I picked some random random theorem in algebraic topology and asked that it should be true here, I took the important structural theorem in algebraic topology and I asked for something that would really control the whole structure of SH prism if it were true. So if you had a prismatic analog of Quillen's theorem, the thing that I mentioned on the previous slide, well, what it would tell you is that in this prismatic stable homotopy category, you have, that tells you have objects that represent, let's say, mod P Syntomic cohomology. And the endomorphisms of those objects, the maps between them, look the same way they look in ordinary algebraic topology, meaning you have some notion of Steenrod operations in Syntomic cohomology, and they behave the same way that usual Steenrod operations behave. And not just for Syntomic cohomology, but for all of their variants, like Prismatic cohomology and de Rham cohomology and so forth. And this has some concrete consequences. So, for example, there's coming out pretty soon a paper of Shahar Karmeli and Tony Feng that use this idea, use these ideas, and in particular the Steenrod operations that you get from this point of view, to see that mod P Syntomic cohomology of FP schemes has some additional structure, and to prove some concrete statements about Brouwer groups of surfaces in characteristic 2. So that's one motivation for why you might want to realize this picture that I'm talking about. Another, it gives you new information about old invariants. It tells you that Syntomic cohomology has these Steenrod operations on it. But another reason is that you can see some new invariants. So a heuristic statement of Quillen's theorem is that there's roughly as many cohomology theories on topological spaces as there are formal groups. And this prismatic version would say that's really the same as you have roughly the same number of p-adic cohomology theories that are related to differential forms. There are, again, roughly as many of those as there are formal groups. So let me articulate this a little bit more precisely. So for now, now I'm going to need to assume that P is odd. I don't quite know the analog of what I'm going to say in characteristic 2. So let me make a definition. Let's say you have a cohomology theory E, which is even, P complete, it's even, meaning the cohomology groups of a point are concentrated in even degrees. And I'll say that it has Adams operations if there's a ZP star action on E, such that if you extract a formal group from E in the way that I described earlier, that formal group is acted on by ZP star via the identity character. So an example would be E could be K theory, and you could take this ZP star action to be given by the usual Adams operations in K theory. So these are cohomology theories that in some sense feel a little like K theory. And this is not really a new expectation. It's a consequence of what I've said so far. If you believe everything I've said so far about the prismatic stable homotopy category, then any ring spectrum E that looks like this is going to have some incarnation in this SH prism, which I'm going to call E prism. And this should be compatible with what I've already mentioned in some important examples. Namely, if E is K theory, you get the prismatic incarnation of K theory. If E is an Eilenberg-MacLane spectrum, you get that object I called Z prism. And if E is mu, you get the prismatic incarnation of mu. And there's a fancier way to say this that involves an object which was introduced by Bachmann, Birkeland, and Zhu. They called the stable homotopy category of F1. This is supposed to be some version of motivic homotopy theory where you don't fix a base scheme. It's some incarnation of motivic homotopy theory that's completely independent of the arithmetic of any base. And it's supposed to map to motivic homotopy theory in any fancier incarnation. In particular, it should map to this thing I'm calling SH prism, which is some kind of stable homotopy category for formal ZP schemes. And so let's say you have a spectrum with Adams operations, and in that case, well, you have this object. It has an incarnation in the prismatic stable homotopy category, and that represents some cohomology theory on p-adic formal schemes. So in the case where E is Ku prism, or sorry, E is Ku, this is Ku prism, that was topological cyclic homology. And so this is what you might think of as the E version of topological cyclic homology. So any spectrum with Adams operations has its own version of TC, and not just TC, but all of the friends of TC. The way that you can compute topological cyclic homology by thinking about topological Hochschild homology and topological cyclic homology and so forth, they have counterparts for the E version as well. And everything, in some sense, is built out of things related to prismatic cohomology. That's the E2 term of some spectral sequence that computes these invariants. And these spectral sequences would reduce to the Bott-Morrow-Schulze story in the case where you take E to be complex K theory. Okay, so that's motivation. Why you get new information about old invariants, you get some new invariants. Now, why should you believe that this story is true? Why should you believe in this stable homotopy category? Well, first, at least when P is odd, I think I can tell you what this category is. I'm not going to tell you in this lecture, but there's a construction of something that it just looks right. It has a lot of the right features. It was based on some ideas that I learned from Arpon and Allen. And it has most of the features, well, here let me not elaborate on that. It has most of the features that I've mentioned so far. The only problem is there's no candidate for the object that I called S prism X. In other words, there's no evidence that this construction has anything to do with p-adic geometry. It's just a definition of a category and not that category is useful. It's a construction of, it's a purely homotopy theoretic construction that uses sort of combinatorial input. So another piece of evidence is, well, I don't know how to tell you about these E versions of THH, TC minus, and TP, but they have algebraic counterparts that are like what you should get when you restrict all of these theories to the de Rham locus. And those counterparts, there's a candidate for what those are. This was introduced a few years ago by Tassos Molinos, Bertrand Toine, and Robel, I forgot his first name. Marco. Yeah, so they introduced variants not of topological Hochschild homology, but of just algebraic Hochschild homology associated to any formal group. And those give you, again, cohomology theories for schemes that look like they should be the de Rham specializations of the cohomology theories that I'm talking about. And well, they just fit right into this picture, that all of the predictions that this picture should give you for what cohomology theories look like on the de Rham locus are satisfied by these definitions. Another piece of evidence, so let me mention a familiar theorem, or a familiar phenomenon that, the phenomenon that starts the theory of crystalline cohomology, that if you have a smooth projective variety over ZP, then its de Rham cohomology depends only on the special fiber because it agrees with the crystalline cohomology of the special fiber. So that's a phenomenon that has a proof in this, or an explanation, you might say, in terms of the geometry of these Drinfeld stacks. That is, if you look at this ZP sin, it's some parameter space for p-adic cohomology theories. There's a point that corresponds to de Rham cohomology. There's a point that corresponds to the crystalline cohomology of the special fiber. And then they're the same point. They're not a priori the same point, but they're the same point by some construction that you write down. And so you might ask or you might expect that the same thing should be true for the enhanced version of ZP sin, or really this is going on in ZP prism. And if that were true, it would make a concrete prediction, namely that if you took these theories that I mentioned on the previous slide, these variants of periodic cyclic homology, that after p-adic completion, their value on R should depend only on R mod p. And this prediction is now a theorem of Arpon. And there's some related work of Sasha and Vadim. Well, it's not quite the same statement, but they proved a version of this over Ku at odd primes. So let me mention, how much time have I got? I should be wrapping up now. So let's say, again, you have one of these cohomology theories with Adams operations. So it should have its own version of TC. And an expectation is that you should be able to define this by p-completed étale sheafification of some motivic incarnation of E. So this is a theorem of Dustin and Akil in the case of K-theory, that TC is the p-adic étale sheafification of algebraic K-theory. And so, if you had a good motivic version of the cohomology theory E, you could not phrase this as a demand, you could turn it into a definition. And so this is something I mentioned earlier. If you really understood motivic homotopy theory in mixed characteristic, or mod p cohomology theories for schemes over FP is really what I mean, then you could turn this expectation into a construction. And all of these conjectures would become theorems. Now, I don't know if you should believe the Hopkins-Morel theorem in equicharacteristic P, but I believe that even if it's false, these theories still exist. You just can't necessarily construct them in that way. And let me just mention as one piece of evidence, so all of the constructions, all of these invariants that I mentioned are, they're speculative. This stable homotopy category, SH prism, you should think of that as it's really some category of motives over ZP, which I don't know how to work with. But more generally, you should have SH prism R for any p-complete ring R. And if R is big enough, then actually I do know how to define these things. And I do know how to construct this entire picture. And what does big enough mean? Well, if R contains a compatible system of p-power roots of unity, and so in that case, you can turn the thing I mentioned on the previous slide to a construction where the input is that you know that motivic homotopy theory works well over the fraction field. And this work that I mentioned of Shakar Carmeli and Tony Feng, it really uses this point of view to construct this theory over ZP cyclotomic. FP is a ZP cyclotomic algebra, and it gives you a good theory over FP. Yeah, so as a consequence, the story that I've told you, it's not speculative as soon as you have a compatible system of p roots of unity. All right, I will stop there. Thank you.